Welcome. Let's start a new lesson on the power rule for derivatives. So we're looking at sections 2.5 and 2.6 today, and we're going to do this one over 2 days. Mainly we'll learn the basic rules today and then expand it tomorrow into like tangent lines and things like that. So here's the basic differential rules. And these will be nice because our way of making a derivative before or finding the derivative was the limit as h goes to 0 of f of x plus h minus f of x over h. And this was defined then as the derivative at x. So general case derivative. We also had a version where we could find it at a point, if you recall, and that formula looked like f of x minus f of c over x minus c, where x was driving towards c. And that one found us the derivative at a point. So today our main focus is going to be learning these shortcut rules so we don't have to do that long limit definition. So the constant rule, the derivative of a constant function is 0. That is, if c is a real number, then the derivative of c ends up being 0. Why would that be? Well, if this is my function, y equals c, how does that graph out? Well, that is a horizontal line at the height of c. And of course, we can see that the slope on that is always 0, horizontal tangent line. All right. Next, let's go to let's do special case one first. Special case of the power rule. No, let's do power rule first, now that I'm reading it out loud. The power rule. If n is a rational number, rational, remember, is a ratio, a fraction. If n is a rational number, then the function f of x equals x to the n power is differentiable. And the rule for the derivative, so this means the derivative of this function with respect to x is, well, you take the power, you put it in front, and then you reduce the power by 1. So that becomes the derivative rule. That is our power rule. N comes down, and then I take and reduce my power by 1 degree. For f to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on that open interval containing 0. That's just kind of a caveat that we must keep in mind. Special case of the power rule. What if I just had x? What would it turn out to be? Well, it turns out that its derivative is 1. And if you think about, if I have the function y equals x, because it's saying take the derivative on the function x, well, that is a linear function with a slope of 1. Oh, it makes sense then that the derivative would be 1, doesn't it? And really, this is just a special case of the general power rule we just talked about, where we said if y equals x, that's a 1 power. The derivative y prime would say what? Take the power, bring it down. So I bring the power down, I have 1 of times x to the power minus 1, because it says always take the power and subtract 1. Well, what does that turn out to be? X to the 0, or x to the 0 simplifies to 1. And that's how we get this special case. Do I really need to memorize the special case? No, because the power rule will get you there as well. But sometimes it's just faster to have it memorized. All right, so we've got 4 examples sitting here for us to do. Let's work through them. F of x equals x to the 5th. Power rule, my power is 5. So let's use our notation. There should always be a left-hand side on these. F prime of x equals. The 5 is going to come down and become a multiplier, and then I have x to the reduced by 1, the power, and I get 5x to the 4th. Okay, that just followed this beautifully, didn't it? The power rule. Make a note to yourself, reduce power by 1. By 1 degree. That helps you remember. Okay, on to b. Oh, b isn't quite as simple, is it? But let's turn it into, instead of a radical, let's turn it into an exponent. So I'd have x raised to the power over root 3/4 power. Okay, now you've identified your n, right? It is 3/4. So to get to its derivative, we'll go g prime of x equals 3/4 comes down, and then we reduce the power by 1 degree. 3/4 minus 1. Now let's simplify, make it look nice. And I get 3/4 x to the, 3/4 minus 1 would be a negative 1/4, wouldn't it? Often you're asked to present your exponents as positive exponents. And if you recall, a negative exponent will drop it to the bottom. And it's a 4th root in this case. So I'm going to write 4 root 4 of x. First 4 coming from the 3/4. Excellent. Next one. Y equals 1 over x cubed. Let's rewrite this into y equals x to the negative 3. Now apply the power rule, which says what? Well, I'm going to say y prime. There's Newton's notation. Y prime, negative 3 will come down. So I have negative 3, x to the negative 3, reduce the degree by 1. And that's going to give me a y prime equals negative 3 x to the negative 4, yes. And then don't leave a negative exponent, so we'll drop it to the bottom so we can write it as a positive exponent. And we get an answer of negative 3 over x to the 4th. Okay, D looks interesting. It is not quite as simple as what we had before. I don't know a product rule for derivatives. At least I don't yet. Soon, that'll be coming our way. Instead, what could we do to this? We could distribute it through. We could FOIL this out. And that's going to give me a y squared equals x squared plus 2x minus 4x minus 8. Simplify one more. Where'd the y squared come from? Y equals. On the right-hand side, let's pull our middle two terms together. And we have minus 8 and a minus 2x. Now, power rule it. We have a nice polynomial. This will be easy, won't it? We get y prime. Remember, the power comes down, 2x, and then reduce it by 1. And this one, the power comes down, negative 2, x to the 1 minus 1, that's going to zero out. And then the derivative of a constant, well, that is 0. So this one took on a different rule. This was a constant. And you can look up above, and we have that rule for the constant. So maybe even just put constant rule. All right, now we're going to simplify. We're going to have y prime equals 2x minus 2. That's it, because this would go to 0, wouldn't it? So for that one, we just wanted to FOIL out so we could get to a polynomial, and then that polynomial allowed us to use the product rule. On the back, or no, on the bottom, it says the constant multiple rule. If f is a differentiable function and c is a real number, then c times f is also differentiable. And the derivative of that function, c times f of x, the derivative of all of this is c times f prime. Basically, you remember like limits? And we had limits of c times f of x, where we could bring the c out front. Well, kind of the same thing's going on here. Just leave c alone and take the derivative of the function, okay? And I didn't put anything down here, right? Whatever the limit was headed towards. So we hit this scalar multiple rule, or the constant multiple rule, and it really just says, kind of work with this. So I'm going to say that I have y equals, well, I have 2 times x to the 7th. This is my function right here, isn't it? X to the 7th. So my product, or my derivative, is going to be the product of the constant times the derivative of x to the 7th, which is 7x to the 6th. Power rule on that. Maybe just go PR if you can remember that's power rule. Now we can take 2 times 7, call it 14, x to the 6th. Would I need to show all these steps? No. You know, as you get faster, you're just going to say, oh, that's 2 times 7, and then reduce the power by 1 and get 14 x to the 6th all in one step. But for right now, you're learning these rules. Take it one step at a time, understand how each step leads us to the derivative. For B, not quite as nice as A because I noticed that my x is in the denominator. So in order to handle that one, I want to rewrite this. So I'm going to have g of x equals 3x to what power? That's right, the negative 2 power. And then I'm going to take the derivative g prime. I have a constant multiplier, so I'm just going to move 3 forward, and then I can bring that negative 2x to the negative 2 minus 1, power rule-less, and simplify. Now I've got 3 times negative 2, or negative 6, x to the negative 3, which really could be written as negative 6 over x to the 3rd. So it was a second down below, now it's a third. It looks like it increases, but really we know it decreased by a power because it became negative 3, which drops it to the bottom as x to the 3rd. Okay, for C, do you see a multiplier? Because often people have trouble sorting this out. This 8 underneath is really like 1 times the radical that we're seeing over 8. I could bring out the multiplier 1/8 and then have it times x to the 5/6. So I'm going to get that power rewritten from radical form into exponent form, pull the multiplier out. Now, derivative time, notice the prime symbol. I'd have 1/8 still forward. I'm going to bring down 5/6, right, because that's the power coming down. X to the 5/6 minus 1. Power rule happening here. So f prime of x equals, to multiply fractions, you multiply your tops and you multiply your bottoms. And then we'd have an x to the 5/6 minus 6/6 if you have to, right? Don't make it easy on your brain. Equals 1/6, looks like it's going to be a negative 1/6. And finally, let's format that into a pretty sense. We'd have f prime of x equals 5 over 48 x to the 1/6. You could write it as a radical if you prefer. And now for D. D, y equals, ooh, what do we got going here? I've got an x to the 1st times an x to the 1/3. Can I join these together? Yes, join by adding the exponents. Now, that's going to give me a y equals x to the 3/3 instead of 1. 3/3 plus 1/3 equals 4/3. And then I'm ready now for the derivative action. See if you can do this one before I do it. So what I hope you came up with is that your 4/3 came down, didn't it? We used power rule on this. Here's our power rule happening. 4/3, x to the 4/3 minus 1. We got to reduce it by a power. Oh, then that gives me 4/3 to the x raised to the 1/3, because what I was subtracting was 3/3. All right. Now, the backside has many, many more examples. I think I'm going to put them on a separate video. Okay? For now, you should be able to do the Delta Math 2.5, 2.6a version, and that should be open for you. So have fun, do a little homework, learn these power rules.